Hello student, welcome to today's lesson 1, where we are going to look at electromagnetic spectrum. We start with the definition of electromagnetic waves. As you can see from this word, it is coming from two words, electromagnetic. So electro is coming from word electricity and magnetic is coming from the word magnetic field. So we have electric field and magnetic field. Now, when the two interact, they give us what we call the electromagnetic waves. So electromagnetic waves are transverse waves, which results from oscillating electric field and magnetic field at right angle to each other. So as from our diagram here, we have magnetic field moving up and down and electric field moving in a horizontal direction, as shown here. So this one is moving up and down, and we have this one that is moving in the horizontal direction. So when the two interact, and as you can see, they are making right angles, the trough for this one and the trough for the other one is making right angle. So that way, they give us what we have, or what we call electromagnetic waves. We have examples. We have X-rays, ultraviolet, infrared, visible light, microwaves, radio waves, and gamma rays. As you can see here, there are only 7. So we have 7 electromagnetic waves. We move to the next part where we are going to look at electromagnetic spectrum. And this one, we can start by saying that this one is divided into 7 major regions. And in each region, it has a range of frequency or wavelength. For instance, if you have radio wave, it has a range of its frequency. If you have infrared, it has a range of its frequency. So electromagnetic spectrum is defined as the arrangement of the electromagnetic waves according to their frequencies. So in other words, when you arrange them according to their maybe increasing frequency or decreasing wavelength, then you form what we call electromagnetic spectrum. So the wavelength ranges from 1 × 10⁻⁶ meters to 1 × 10⁻⁻14 meters, which implies that the wave that has the longest wavelength ranges from here, and the one that has the shortest wavelength is at this point. So for us to remember the 7 waves, we have the hint, or what we call the mnemonics. We have roast maize is a very unusual Christmas gift. So R representing the radio wave, M representing the microwave, IR representing the infrared, V representing the visible light, UV representing ultraviolet, X representing the X-rays, and G representing the gamma radiation. So the way they are arranged, R has the longest wavelength, while G, or the gamma, has the shortest wavelength. But when it comes to frequency, gamma has the highest frequency, and this one has the lowest frequency. So you can be able to remember all these using this link or hint. Then from there we move to properties of electromagnetic waves. First, we note that they are transverse in nature. So in other words, the vibration of particles is at right angle with the wave motion. In other words, it has troughs and crest. Then they do not require medium for transmission. They are not like what we call the mechanical waves. These are electromagnetic waves, and they can move through vacuum. They do not require medium for transmission. Then we have that they travel through space with the speed of light, and the value of the speed of light is 3 × 10⁸ meters per second. They carry no charge, and therefore when they move through an electric field or magnetic field, they will not be affected. They undergo interference, refraction, diffraction, refraction, and polarization effects. They possess energy, and the energy is given by HF, where h is the Planck's constant and f is the frequency. H is a constant, therefore it has its value, and its value is given by 6.63 times 10 to power negative 34 joules second. They obey the wave equation, that is V is equals to lambda frequency. But here we are using C, where C is representing the speed of light. They can be emitted, transmitted, and absorbed by matter. From there, we can look at examples. 1. We have a very high frequency radio transmitter broadcasts radio waves at a frequency of 30 megahertz. What is the wavelength? We look at what we have. We proceed as follows. V is equals to lambda f. So from here we can make our lambda the subject of the formula by dividing through by f both sides. We have lambda is equals to V over f. After getting that formula, you just substitute. We have the numerator having the speed of light and the denominator having the frequency. So key in your calculator, putting the bracket, then you put the numerator, then bracket, you put in your denominator. Then from here you can see that the per second is cancelling out because hertz is the same as per second. So when these units cancel out, you are left with m for meters. So after using your calculator, you'll find that the wavelength is 10 meters. We proceed to the second example. Calculate the frequency of a radio wave of wavelength 150 meters. Again, we are applying the same formula. V is equals to lambda f, but here now we make f the subject of the formula by dividing through by lambda. So we have that f is equals to V over lambda. You substitute. V is the speed of light and lambda is the wavelength. So by substituting and putting or keying in your calculator, you find that your frequency will be 2.0 times 10 to power 6, which is the same as 2 megahertz. Then we proceed to that example. The energy of X-ray is given by this one. Given that the speed of light is 3.0 times 10 to power 8 meters per second, and the Planck's constant is this one, find the wavelength of the X-rays. We start with the formula E is equals to HF. From this one, we can be able to get F. F is equals to E over H. So by substituting the values, we have 1.989 times 10 to power 14 as our energy. Then our Planck's constant, 6.6 times 10 to power negative 34 joules second. Remember, energy is given in joules, so the joules and joules will cancel, so you will be left with per second. So by dividing, keying in your calculator, you will find that your F is 3.01 times 10 to power 19 per second. Then from there, we know that C is equals to lambda frequency. So we can be able to get the lambda because our question is asking about wavelength. So our lambda will be C over F. We substitute. C is the speed of light, 3.0 times 10 to power 8, then divided by the frequency that we have calculated here. After that, and keying in your calculator, you will find that your frequency, or not your frequency, but the wavelength will be given by 9.96 times 10 to power negative 12 meters. Then example number 4. A radio is tuned into a radio station 144 kilometers away. How long does it take a signal to reach the receiver? B. If the signal has a frequency of 980 kilohertz, how many wavelengths in the station away from your receiver? We proceed as follows. Distance is equals to speed times time. But now we want time because it is asking how long. So time will be given by distance over speed. So our distance is 144 kilometers. We change it to meters, which is 144,000 meters. Then we divide by the speed of light, which is the speed of our wave, which is 3.0 times 10 to power 8. When you divide, you get that the time will be 4.8 times 10 to power negative 4 seconds. Then part B, we are being asked about the number of wavelength. So first of all, we need to get the length of one wavelength. And wavelength will be given by c over frequency. So we get our c, which is the speed of light. We divide by the frequency. You get 306.1 meters. This is the length of one frequency, one wavelength. So one wavelength is equals to 306.1 meters. How many wavelengths are there in these kilometers? That is 144 kilometers. So we cross multiply and we get the value of x as 144,000 meters divided by 306.1 meters. You get that we have approximately 470 wavelengths. From there we have the assignments. These assignments are just testing what we have just learned. So make sure that you practice. After practicing and discussing with your peers, then come and attempt the assignment. Thank you, and let us meet in our next lesson.